Hi everyone, I'm Nathan Little with Colin Kirby. Welcome to our second evaluation presentation, Retail Analysis Using Neural Networks. We spent the last few weeks debugging and refining our object detection pipeline to improve accuracy and reliability, especially in very dense, crowded retail environments. And today, we're excited to walk you through how we did that, what went wrong, what we fixed, and what's working now. Here's a quick breakdown of what we'll be covering today. We'll start with the project recap, just to bring everyone in on what we're building and how it works. Then we'll walk through our baseline performance, including some issues from Eval2 and how we reset the baseline properly this time. After that, we'll dive into the heart of today's presentation, the improvement techniques. We'll cover 5 major updates we made to the model, why we made them, and what kind of impact they had. We'll also show a comparison between our new baseline and prior results, followed by some highlights in the results section. We've also got a short demo showing the model in action, and finally we'll wrap up with our team's contributions and conclusion. Let's get started. Our goal in this project is to detect and localize individual retail items into crowded shelf images. Basically, teaching a model to draw boxes around each product. This involves working with a dense dataset called SKU110, where the scenes are packed, objects overlap, and accurate detection is challenging. To handle that, we built a custom object detection pipeline with a focus on improving anchor coverage and training stability. The diagram below gives a simplified view of how images move through our system, from loading the data to feature extraction to generating candidate boxes and training the model to make accurate predictions. Our initial setup in Eval2 was all about just getting something to show up. The goal was simply to make the model output anything. The anchors weren't well aligned, and most of our metrics were either zero or so low that they weren't meaningful. We had a ton of predicted boxes, but they didn't actually match the ground truth, or in other words, the real labeled items. Because of this, our loss curves didn't reflect true learning, and precision recall plots were basically just random noise. That's when we knew we had to reset and establish a new, more stable baseline, one with clean anchor coverage and trackable training behavior, so that any future improvements could be measured properly.
So after the messiness of our proper output in evaluation 1, we ended up taking a step back and taking a hard reset and decided to rebuild with a new proper baseline. The goal really was to simplify the architecture and then scale back up from there, with a focus on the anchor generator and its ability to align with the actual object sizes. This gave our model a much more modular training behavior that we could then actually analyze. And just looking at the graph on the right, you can see a major difference with the losses from our evaluation 1, considering it was basically 0 and the losses really meant nothing. But even though the box loss is still high in this metric, it is steadily going down, which tells us that our model is learning to localize better. And even though it's not really perfect yet, the setup is much more stable and gives us a more reliable launch point to begin testing real improvements. So at this point in the project, we knew that our model wasn't really performing well. We had almost no detections, and even though our losses were okay, our predictions were really just not. So to fix this, we wanted to approach the problem from 5 different angles that really covered the entirety of the project, from model architecture to training stability. So as shown in the below, consisting of, like the anchor tuning fixes, our improved matching logic, our box delta debugging, memory and batch tuning, and loss balancing and schedule optimization, which we'll get into more in the following slides. But each of these techniques help target a known bottleneck in our model. So together with the tuning memory, batch sizes, and overall our training schedule, these improvements help lay the foundation for actual learning to then happen. Right, so in our early setup, our anchors, which are basically just the preset boxes that are used to guess our object positions, were just a little bit too small and clustered towards the center, as you can kind of see in that before image. This meant that when we were aligning the boxes, we were rarely aligning with the actual labeled items, which are held in their ground truth boxes. So what we did to fix this was we increased our base sizes and tweaked the scales and aspect ratios so that our anchors now cover a wider range of object shapes and sizes. You can see that in the code snippet in the top. And now, after that, you can see that they're placed more evenly across the image. As you can see in the after image, it takes up the entire image, and it's not like modular. It takes up little bits of pieces of the shape, but it gives us a better overlap of the products and way more useful training signals. So in the beginning, as said in the previous slide as well, the anchors gave us a lot of issues with them not really getting aligned with the ground truth boxes. They weren't actually getting assigned either, which is what we're going to get into in this. But that meant for this, that if the model was making predictions, we didn't really know if they were connecting at all with the ground truths, which then gave us no clear feedback to train on, which ended up causing some of our testing metrics to come out flat and zeroed out, like MAP or precision and recall. It gave us nothing. So to fix this, we rewrote our matching logic with an IOU-based matching instead, with a more tunable threshold that we can then adjust if we want it to be more tolerant or less tolerant. But furthermore, we actually force assign ground truth boxes to its best anchor. So even if the IOU wasn't really high, which is expected in early training, it guaranteed that every object was then represented. From the start, box deltas gave us a lot of issues. From our early visualizations, we saw a lot of predictions that were either making the boxes way too big or just clustering them on the edges of the images. This was occurring because when we were applying our box deltas in our calculations, or the adjustments that we want to make to the predictions in simple terms, is that we didn't really have any safety checks, such as like clamping the boxes to a more safe image size boundaries. So to fix this, we did exactly that. We added a safeguard that clamped the deltas to reasonable limits within the image size, like width and height, and it forced the boxes to stay within those image bounds. And this filtered out any predictions that were either way too small or too massive. This helped keep our predictions simple and significantly reduce the noise of our predictions. At one point during our training, we kept both running into an issue with CUDA out of memory errors. This was happening when we tried to train on like larger data sets with large batch sizes like 16 or 32. And from further debugging, we actually found out that it wasn't really just the batch size that was causing this. Some of our anchor tuning had also exploded our anchor count, which made our memory usage even worse, as you can see on the figures on the right with like 100,000 anchors versus just like 40,000. So to fix this, it really was relatively simple, but we definitely overlooked it. It really was just to reduce our batch sizes, and then we also introduced a subset config that allow us to run smaller amounts of images that we choose to set. So like 100 images versus like the full data set, which was like 8,000 or something. So we also retuned our anchor sizes as well and aspect ratios to limit the number of anchors per level. And this not only fixed our memory crashes, but made our training so much faster. In the early stages of our training too, we began to notice that our class loss and box loss were both on completely different scales, with our box loss often being 10 times larger. This would cause the model to over-focus on one objective, and it led to more unstable learning, where it then either plateau too early or fluctuate too much to properly converge. So to fix this, we explicitly weighted our losses, treating classification as the main drive and then downweighting the box loss to 10%, as you can see in the code snippet on the right. And some further improvements are also extending our warm-up phase so that the model could then ease into training, and then furthermore softening how quickly our learning rate drops. And these both help create a smoother loss curve, especially for box loss, which we'll see in some of the following slides. Before any of our fixes, the model really looked okay from the values. We had a 3.5% precision, 13.5% recall, and some 8 MAP. But when we looked closer and we realized that it was producing over 55,000 predictions for just the 14,000 actual objects, basically what it was doing was just spamming boxes hoping something would hit. And that inflated the metrics like the IOU and F1 without a real understanding of what's going on with the model. So after finding this out and then we began to implement our improvements, the model became way more selective. Box loss dropped significantly, even though you can see on the graph on the right. And even though our recall also dropped and we were only making 861 predictions, it means our model is much more confident and less noisy. And this is the trade-off that we kind of wanted to see in early into tuning. Fewer guesses, but better guesses. So getting into our results and our summary and comparing where we've gained and what we've improved and what has changed, with our self-vision model, which is what we named it. Compared to our Eval1, we made some real progress. We now get non-zero detections with a precision of about 2% and an IOU of about 0.38. And this means that our predictor boxes are starting to line up with the ground truth or the actual labeled objects. And even though confidence is still low and behind state-of-the-art models like YOLO v5, the key takeaway is that our model is no longer completely failing on the test set and it's actually making meaningful predictions. This forms our benchmark moving forward as we compare against some of the pre-trained models like the YOLO v5 trained on the Coco, and then the fine-tuned version, which we'll break down in the next few slides.
This chart comparison shows why domain adaptation matters. YOLO v5, when pre-trained with Coco, has never seen any dense retail shelf layouts, so it doesn't know what to look for in SKU 110K style images. It either predicts objects that don't overlap with ground truth, those are the real labeled boxes, or it gets filtered out entirely during post-processing. Shelf vision, on the other hand, while still in early stages, is at least showing some meaningful overlap. Our IOU is non-zero, MAP is beginning to rise, and we're making progress. So even though raw recall is low, the takeaway is that shelf vision is already starting to adapt to the retail domain, something YOLO v5 can't do without fine-tuning. Here, we're comparing our model to a fine-tuned version of YOLO v5, trained specifically on the SKU 110K dataset, something that it's weak in. As you can see, YOLO dominates across all metrics. It's learned how to localize and label retail products really effectively, and its predictions are both dense and accurate. Shelf vision falls short because it's a lightweight custom architecture. It's optimized for speed and lower memory use, not maximizing detection power. Plus, we didn't do nearly as much hyperparameter tuning as YOLO, and we're not leveraging features like multi-scale detection. So while our model is improving, it's not quite on the same level yet, and that's expected. For this project, we divided the workload based on our strengths. Colin shined as a programmer and focused more on the architecture and core implementation. handling the backbone, detection head, and custom anchor logic, while I took care of the evaluation, debugging, and analysis. Colin also developed most of the visualization tools, and I handled a lot of the writing and metric interpretation. For training and tuning, we split responsibilities pretty evenly to troubleshoot loss behavior and prove stability. It was a very collaborative process, and each of us played a key role in pushing Shelf Vision forward. Shelf Vision has come a long way since Eval1. We now produce valid detections with significantly better bounding box alignment. Our average IOU has jumped to around 0.38, which is a solid sign that the model is understanding where objects actually are. While precision and recall are still low, that's mainly because of confidence filtering and issues with borderline box predictions. Fine-tuned YOLO v5 still clearly outperforms us. It's trained on a much larger scale and benefits from a more robust architecture, but what we're seeing is meaningful progress. Shelf Vision is starting to generalize to real shelf layouts, even under tighter constraints. In terms of next steps, we want to dive deeper into the false positives and see which predictions are getting filtered and why. We're also planning to look into threshold tuning and augmentation strategies to help boost recall. And finally, we do need to start the final report. That's something we haven't kicked off yet, but it's now a top priority.